Okay, Eg6. Given that y equals x squared minus 4 cubed, find the coordinates of any stationary points and determine their nature. So we know we need to differentiate for that. We've got this embedded function. We could expand it using a expansion that would give us something we could differentiate using AS skills because it's cubed, but it's going to be easier to use chain rule. So we take our embedded function and we differentiate that. 2x. This means that our original equation now becomes u cubed, and when I differentiate that, I get 3u squared, which once I've finished the differentiating work, I can substitute back into, gives me that. So chain rule, dy dx is dy du times du dx. So that'll be that times that, which gives me 6x bracket x squared minus 4. So I want to find the coordinates of any stationary point. So it's dash at stat point dy dx equals 0. So 6x bracket x squared minus 4, lost the squared there, all squared equals 0. So either 6x equals 0, which will give us x equals 0, so I got a stationary point at there, or x squared minus 4 all squared equals 0, which means x squared minus 4 x squared equals 4 square root x equals plus or minus 2. So I got stationary points at 0, negative 2 and positive 2. To work out what they are, I'm going to substitute into 1. So sub in 1 for y coord. So x equals 0, y equals, so on our calculator, if I store 0 in x and then do x squared minus 4 close bracket cubed, I get minus 64. If x is negative 2, y will be, so I'm now going to store negative 2 in x and then go back up to that and I get 0. Then if x is positive 2, so I'm now going to store 2 in x, 2 store x, and then go back up to the function and put 0, 2 in there, we're also going to get 0. So we've got start points at minus 2, 0, at 0, minus 64, and at 2, 0. So finally then I need to work out the nature of those stationary points. So I need the second differential, so I need d2y dx squared. If I go back to the dy dx, I can expand this out. I got the 6x, and then the x squared minus 4 all squared. I can just use GCSE skills to multiply that. You square the first, it's x to the 4. You square the last, it's plus 16. And then the middle term is twice the product of what you've got. So minus 4x squared doubled is minus 8x squared. So dy dx will be 6x to the power of 5 minus 6 eighths are 48x cubed plus 6 times 16, 96x. So I now need to differentiate that a second time, and I'm going to get 30x to the power of 4 minus 48 times 3, 144x squared plus 96. So when x is negative 2, so going back to my calculator, storing minus 2 in x, and then I want 30x to the power of 4 minus 144x squared plus 96. So d2y dx squared is 0, so that's inconclusive. At x equals 0, I can see d2y dx squared, that's going to be 0, that's going to be 0, that's going to be greater than 0, so a max, sorry, throw minimum. And when x equals 2, so store 2 in x and go back up, it's equal to 0 as well. So at x equals 2, d2y dx squared equals 0. So I now need the third differential. So d3y dx cubed so that will be 120x cubed minus 288x. So when I put x as minus 2 into that, I want it not to equal 0, or I got problems. So minus 2 store x, 120x cubed minus 288x is not equal to 0, so point of inflection, and at x equals plus 2, so store 2 in x, go back up to the function, it's plus 384, it's not equal to 0, therefore point of inf. So to summarize, therefore we have a minimum at the stationary point 0 minus 64. We have a point of inflection at minus 2, 0 and 2, 0. And if we want to have a look at what that looks like graphically, just find my GeoGebra. So going back to the original equation of the curve, I've got open bracket x squared minus 4 outside the bracket to the power of 3. Okay, and then if we zoom in, we can see we've got that minimum value there at minus 64. And then coming down to the axes, you can see the 2 points of inflection really nicely. So that's great. So that's a stationary points question.